We're here today to talk about the stormwater benefits of rainwater harvesting. I'm Dr. Peter Coombes. My expertise is systems analysis, but I've done a lot of work on rainwater harvesting. I was recently I still am the editor of the Urban Book of Australian Rainfall and Runoff published by Engineers Australia, so this is quite topical for me. And we're having a bit of a chat about stormwater harvesting and the relationship with stormwater management, the relationship with rainwater harvesting, because it's quite a contested area. So I'm showing some slides as well during this talk to explain the concepts and show the concepts I'm talking through. The first issue I want to talk about is the impact of rainwater harvesting on the stormwater management processes. Rainwater tanks or rainwater harvesting at the local scale at households mitigates local flooding, so that's the flooding immediately below your house. And flooding is not just big river floods. Flooding in an urban area is anything from small events that get your feet wet, which is what councils spend most of their money on to build stormwater pipes and gutters in your street, all the way through to the very large river flooding events. So when we're talking about flooding, we're talking about the whole spectrum of flood events that are really being managed using quite a lot of money in urban areas. So the common false perception about flooding is it's only about large river floods, but most of the money in Australia is spent on the small flood events in urban areas. These are the things that rainwater harvesting and other small scale, lot scale, household scale measures can alleviate. Rainwater harvesting has the capacity to supplement the capacity of drainage systems. They're the pits and pipes in your streets that dispose of the stormwater from smaller events. They don't protect you from large flood events. The council drains or the pits and pipes actually manage up to moderate stormwater events, so you don't get your feet wet, cars aren't washed away, there's no property damage and there's no risk to life. Also, rainwater harvesting can decrease the transfer of contaminants to waterways, so they're the pollution that can travel from urban areas through drainage systems and urban waterways and then onto estuaries and bays such as Moreton Bay or Port Phillip Bay. Transfer of nitrogen and phosphorus, for example, are pushed along by the volumes of stormwater runoff into waterways, and they can be quite damaging throughout most countries. Also, if we reduce the regime of flows leaving properties, we also reducing the accumulation of volumes and flashiness of flows as stormwater flows down catchments, and that reduces the erosion and sedimentation in urban waterways and local rivers. And sediments entering bays and estuaries and rivers actually coat, for instance, seagrass that fish rely on to live and support the beginning of the food web with sea life. So the coating and the smothering of vegetation, sea vegetation and river vegetation with sediments, for example, can actually cut off the beginnings of the food chain for aquatic wildlife. And ultimately, rainwater harvesting can contribute to improving the quality of water in our waterways and bays. So how this works, and I've got a picture here that we'll look at. First of all, we've got a house that will have a rainwater tank that will be connected to a roof, and some of the runoff, rainfall that falls on the roof, the rainfall runoff, will flow via the roof surface into the gutter system, down the downpipes, into your rainwater tank. Some of that water is stored on site, depending on how much indoor use you have, and some of it will overflow into your street drainage system, which is the street immediately out the front of your house. So the reduced flows from your house because of the rainwater tank will be reduced flows in the drainage system out the front of your house. So in the front of your house, it's often misunderstood. The drainage system that's to protect you from moderate and minor events in your street is actually the road gutter, and the pits and the pipes under the street. It's often conceived it's only the pipes, but it's actually your road that conveys most of the bigger events. So if you're reducing the amount of stormwater that persistently flows onto the road and then into your drainage system, you're changing the need to maintain and replace the roads because of deterioration of the road surface is decreased, and you're also freeing up capacity in the drainage system. Then as the stormwater travels down the catchment in your drainage system, pits and pipe system, it will often flow into a major drainage system or a big system. It might be an open channel, it might be an urban waterway, it might be a larger pipe, and hopefully there'll be a gross pollutant trap, maybe a constructed wetland to clean up the water before it enters an urban waterway or a bay or a receiving water now, or a local river. So this is quite important. So if the frequency, the regime, so and the volume of stormwater, if it's reduced flowing to these devices, say the wetland and the gross pollutant trap that cleans up the water quality, the maintenance regime and the life expectancy of these devices last longer. So that's basically some of the benefits of rainwater harvesting. It also reduces sediment and erosion in the urban waterway, and that changes the flow regime of those contaminants from the urban waterway to the receiving water. So the rainwater harvesting system on your house exists in an entire system. I'm now showing a slide of a traditional stormwater management system, and it's not really just stormwater management. If you see this, showing a catchment of which letters A through to G and H, which might be a city, say Brisbane or Melbourne or parts of a city. It's got some traditional drainage system, which is pipes and so in there that are taking the runoff from roads and properties, including your house, and putting it into an urban waterway, and eventually at the bottom of that catchment there'll be a constructed wetland or a detention basin that takes the water and slows down the flows before it enters a river or a waterway or receiving water. But at the same time, that urban area is taking water from a catchment somewhere else, usually a rural catchment, which farmers and others rely on for water supply. So by doing that, it's actually changing the environmental flow regimes in the river below that rural catchment, and it's actually the city's taking water from the rural area. So there's actually a hidden trade-off going on here that people are not aware of. And if your city is struggling for water supply, and it's only reliant on dams, it may also be reliant on desalination from an ocean, which is fairly energy intensive, to supplement that supply. Also at the bottom of that catchment and throughout that catchment there's a wastewater system, and wastewater systems, surprisingly to most, are actually designed to carry stormwater. So they have a peak design. And these systems are cumulative, so the red hydrographs, as they're called, with the first one is allotment, is the shape of the stormwater runoff that will run off one property, say your house, and then there'll be further down the system, you've got two houses come in together. This is the red shapes, red graphs, so then you've got two volumes of water coming together. And then as you go down the catchment to the sub-catchment, that shape of that and the volume is greater until you get to the bottom at point D, where it's actually society's trying to manage this thing. you get a large volume of stormwater that enters that system. So these graphs are volume and time, which engineers call peak discharge. But as you can see from those shapes, there are a volume of stormwater that we're attempting to manage. So in essence, this slide is all about an integrated system we're trying to manage, which stormwater is part of. And when we live in an urban area, we're actually taking and relying on resources from other areas, including rural areas and so on. So if we're managing stormwater, say using rainwater harvesting, we're actually changing the impacts on other people's catchments, for instance those where farmers live in potentially, and changing impacts on the energy system by demanding less desalinated water. This slide shows something that is quite important in an urban area or in any infrastructure equation, but let's just say the stormwater system in your urban area, it's built to perform in a pristine manner, but throughout time its condition deteriorates, which is the red line on this graph. It's known as the structural condition and age on the bottom of the axis, on the horizontal axis. So over time, the condition of the asset, in this case it'll be the pipes and the inlet pits and the road asset and the curb and channel that discharge this stormwater from your urban area to a catchment to protect you from nuisance and property damage. It loses its capacity to do that over time, which is shown by the hydraulic capacity shown as the green line. So after about 30 years, there's a strong decline in the capacity of the system. And that's actually created by blockages for tree roots. Most of your stormwater systems are butt jointed. They move because soil moves. They become blocked and misaligned. There's all sorts of issues that go on with them over time, including become cracked, that changes their ability to perform. So one of the opportunities with rainwater harvesting is, rather than go out and build a whole new set of infrastructure because your infrastructure is getting old and losing its ability to perform, you can actually change the volume of the runoff that's entering the system so that you don't have to replace your ageing infrastructure.
So Peter, that slide is showing that after 30 years, the performance of the stormwater system actually decreases quite sharply, and then really reduces down to something like 40% over 100 years.
That's true. So obviously the new stormwater systems are good for 20, 30 years before they start changing their performance, and then the decline is reasonably rapid, which is expected. We should also add, when looking at this graph, say in the city of Newcastle, the average age of their stormwater drainage system is about 60 years. If we look at a city like Sydney, the average age is changing rapidly because of the urban expansion which also involves a lot of new stormwater infrastructure, say for Melbourne, say for Brisbane. But the average age of their infrastructure is anywhere between 50 and 90 years, depending on where you are in the city. So if you look at that graph, you can see that the loss of capacity we're dealing with. But also, the second slide is actually showing something quite important. The density of the city, the hard surfaces, engineers call it the impervious surfaces, don't stay the same throughout the life of a city. So your stormwater infrastructure was designed for a certain density. It's back in the days often when houses had backyards and lawns and trees and things. In the modern era with McMansions and houses taking the majority of your properties, a lot of that green space and trees, unfortunately, and it's become hard surfaces. So that's increasing density of the city, which is the red line showing there with increasing with age, worsens the effect of the reduced hydraulic capacity of the stormwater systems. So you've got a double whammy happening there. You get lost capacity in your existing infrastructure that you're relying on, and your city's getting denser and denser. It's more and more hard surfaces as we're trying to put more people in smaller areas. So your infrastructure is losing capacity, but it's now coping with inputs that it was never designed for. So that is an opportunity for changing the way stormwater runs off properties. The outcome of those two issues, we've lost capacity in our stormwater systems and increasing density of the cities, is massively increased flooding and rapid decline of waterway health. That means your urban streams, if you still have them, your local wetlands, your local river, your bay, your estuary, they're impacted by these higher stormwater runoff flows that cause erosion, sediment, and also carrying pollution. So there's a lot of pretty poor outcomes from these increased flows in urban areas. Please note it's the opposite for a rural area. So in rural areas we're arguing about losing flows. For instance, in the Murray-Darling Basin we don't have enough flows, and we're arguing about environmental flows and we need more of them. In an urban area we can have far too much flow, which creates all these problems I've just talked about. So it's very important to know the difference between the rural problem of environmental flows and the urban problem of drowning our urban systems in too much water, which is what we're doing. I'm actually got a slide here now. I'm trying to talk about stormwater management with local rainwater harvesting, and I'm introducing the concepts of scale, integration and cumulative impacts. The first thing you should be aware of that everything we're doing in an urban area is connected to everything else we're doing. Sorry, I'm a system scientist, but that's the reality. And everything that happens is not average, it's cumulative. So what happens in your property might not seem much, but if you're in the top of your catchment and the water from your property flows past all these other properties are doing the same thing as you, as the water flows down past other people's properties, what happens is you get a clear cumulative effect. And this is actually was shown previously and it's shown here as well in now the red and the blue hydrographs that we call them. So just say, for example, you have a rainwater harvesting system on your property and it reduces the volume flowing off your property. So that's the little red bit in the hydrograph on the allotment graph. But it doesn't reduce the peak flow, which is the maximum height of the graph, but it reduces the volume flowing off your property, which is a common argument made by engineers because they like to think in peak flows, although that's now changing. In international science says we have to manage stormwater by thinking about volumes. So your property is taking some of the volume of the stormwater because of your rainwater tank, but it's not reducing the peak flows. So that's a worst case. As you get to the second property, as you go down with the two shapes coming together, you get what's known as sawtooth hydrographs. So you've got two volumes missing, two parts of the volumes missing from each property as it's coming in to, say, your drainage system. And as you get further down, as we call a subcatchment, you now see the blue shape compared to the original red shape is flatter, it's got less volume in it, it's less damaging to the environment and less flood risk. So the blue height versus the red height in the graph is showing the peak flow is far lower and the extended hydrograph, as its timing is longer, horizontal axis is time, is actually showing that the water's being released more slowly by simply saving some of the volumes on each property. And so it's what's known as a cumulative or scale effect, and the volume is less. And as we get right down the bottom at point D, you can see the final graph at the bottom of the catchment. We had the original very high volume and peak flow red shape has now been changed to the blue shape, which is closer to what the environment expects. It's far less damaging to the environment and humans, and the volume is less. So there's less to manage. But in so doing, we're also taking, if we're using that water, we're taking more water from someone else's rural catchment via our dams for our city. So we're actually producing a benefit to rural communities by taking less water. And that also produces a benefit at point B on the river, where it's improving the rural environmental flows, which we need to do by managing stormwater and reducing the flows in an urban area. So we're actually creating this benefit that people don't often talk about of changing improving environmental flows in rural areas by reducing the runoff in an urban area. That's what rainwater tanks do. But we also have to consider the context, which is, say, I've taken subcatchment G here, and in a modern urban planning concept, we've got demographics going on there, different soil profiles, hopefully different vegetation. We want to change our heat island effects to mitigate climate change. So hopefully we've got more green stuff in there, plants and trees that work together with the rainwater harvesting to improve your urban area and make it more livable. So that the rainwater harvesting strategy in your house is not working on its own, it's producing a cumulative effect that benefits even rural communities, and it's also working together with the other things your society's trying to do to make your urban area better. So I did some auditing for the Queensland Auditor General via the Queensland Water Commission back then when they had one. And there was an argument about, well, why would you have water efficiency and rainwater harvesting? It doesn't seem to be a lot of benefit. The graph I'm showing now are average results for sure, but this is from real data. And we live in a world where people say a lot of things, and in the rainwater harvesting industry and the sustainability industry, there's always a lot said about what works and what doesn't, but in data I trust. So here's some data. On the one side here is houses with no rainwater harvesting or water efficient appliances. It's their water use patterns. And this is 18 months monitoring of the water use events and the flow rates for each water use event. So number of events versus flow rate. On the other side is houses with rainwater harvesting and water efficient appliances. It's their water use patterns. And as you can see, the amount of water used per event. Now an event in a household might be flushing the toilet or having a shower or watering the garden. That's a water use event. Washing the dishes, I try and avoid that. But anyway, what's happening here is water demanded from households in Queensland, as we actually measured it for households without rainwater harvesting and water efficiency and those with rainwater harvesting and water efficiency. And as you can see, the shape of their water use is dramatically different. So when that part of the water use that's used for indoor use is regularly drawing down your rainwater harvesting storage, your rainwater tank, leaving space available for the next time it rains so that you're also managing your stormwater runoff. So these graphs are about water use, but to have a stormwater benefit from a rainwater tank, you must use the water. And if you use the water for indoor uses, you've got a guaranteed stormwater benefit. Like a constant indoor use like a toilet, provided your system's working properly, produces in combination with other uses that actually draw down your rainwater storage, actually creates quite beneficial outcomes for stormwater. So in an urban area where your rainwater harvesting system is backed up by mains water from your utility, say a Brisbane Water or a Melbourne Water, the best rainwater harvesting system is one that empties often. It's the opposite to thinking about rural areas. So if you draw down your system often, it means it'll be available to fill up more often and have storage available to manage stormwater more often. So that's how you maximise your benefit. So the design of rainwater harvesting in an urban area with backup from a water supply is to not worry about keeping it full. You try and keep it empty by using the water for indoor uses as much as possible. Clearly not overuse the water, but realise the design is different. So to maximise your stormwater benefit, you actually need an indoor use. A few of them would be really good on top of your outdoor use. And you also need to ensure that you're emptying or drawing down your storage regularly. So constant indoor uses like toilet flushing are really good for stormwater management. This slide is about a house in the inner city of Richmond, which my colleague Chris Walsh, a scientist. So his house has 2 slimline rainwater tanks, about 5.5 kilolitres, 5 5,500 litres of rainwater storage. He supplies toilets and laundry. And importantly, his rainwater tanks overflow when they get full into his edible rain garden, his kitchen garden, and then flows to the street. So it's quite important because the rainwater harvesting is part of the other things you're doing on your property. Shouldn't be considered in isolation. He saves about 40,000 litres of rainwater supply each year, so he's not demanding that from mains water. And if we see the first graph, the grey, which is monthly runoff volumes from his property, the grey and the black bars are actually the total volume each month added up flowing from his property. But the grey part of those graphs for each month is the volume of stormwater that's no longer flowing from his property into the street drainage system. And that's quite important because before there was an urban area in place in that area, the majority of stormwater would not have run off a natural environment. So what Chris is quite passionate about is trying to reduce the runoff from properties down to what nature expects rather than all the excess water that urban areas generate. As you can show there with the black bars in the graph versus the grey, his house has dramatically changed the runoff. If we go over to the other graph, it's the runoff days per month, and that's an assessment measure that many people use to assess environmental performance. And as you can see, he's reduced runoff days considerably for part of the year and noticeably for the other part of the year. So his house is saving water, saving impacts on the council infrastructure that's protecting people from flooding and nuisance and property damage, and he's also protecting his local waterway in Port Phillip Bay.
Peter, that also doesn't take into account what actually happens in his garden as well, because that's only recording what's coming out of his house.
And that's a very important issue because this rainwater overflows into his garden and uses his kitchen garden, and something like 40% of his kitchen food demands are now supplied from his kitchen garden. So it's actually produced this extra benefit. And if you take that further, Mike, he's also using that to create shading in his property to mitigate the heat island effect, because he lives in an inner city area which is all concrete. So he's actually getting reduced heat island effect, the rainwater supplying the vegetation to keep the shade canopy in place, and also supplying his kitchen garden, which is offset some of his food miles. And so there's a number of benefits of considering the household rainwater system. This is my own house, which is in Carrington, New South Wales, and I like collages of pictures. It makes it real. It's the longest monitored house possibly in the world for rainwater harvesting and sustainability. It's been measured for everything that moves in this house. It's been measured for more than 20 years, including the rest of my family, which has annoyed them a little bit. You know, when did you flush the toilet and so on. However, it has taught us a lot. It's showed us some new things we didn't understand, because we always learn new things, but also showed us the many myths about sustainability that impact on people. And in many areas, like rainwater harvesting, there are many myths that people act on, and it's dismissed some of those. This unusual house, because it's run by solar batteries and solar panels, it's got a low energy e-pump supplied by Mike. It's got a 5,000 litre slimline tank. It's a small inner city property like that of Chris Walsh's I showed on the previous slide. The conventional wisdom 20 years ago when I put it in was, oh, you can't do rainwater harvesting or a kitchen garden for that matter, or have effective solar panels on a small inner city property. It can't work. Well, this is one of the smallest and it works quite well. But I want to focus here on how the runoff for every event has been reduced from this small property. So the graph here is a bit unusual. So the actual runoff from the property. BAU runoff is what would have happened on the vertical axis, and runoff on the bottom axis is what has happened. The red vertical line is what has happened, and the blue dots is what would have happened as we've measured if the rainwater tank wasn't there and the kitchen garden wasn't there, and so on. As you can see there, there's on all rain events, there's dramatic changes of stormwater runoff from this property. On average, there's a 55% reduction in stormwater runoff volumes. Some of my roof and my front veranda and yard discharges directly to the drainage system, so that's not managed by the rainwater tank. The most contested chestnut in rainwater harvesting and stormwater management is the tank's always going to be full when it rains, therefore there's no benefit. This graph now I've just shown you with the green triangles on there shows the available storage in the rainwater tank prior to each rain event we've monitored over that very long time. So on average in that 5,000 litre storage, there's more than 2,000 litres available to store stormwater before a rain event. So the tank is hardly ever full, if ever, prior to a rain event. And quite ironically, it's always nearly empty prior to the large rain events because they tend to happen in summer during thunderstorm periods. And that's the large rain events intense rain events create the flood risks. So it's sort of dismissing a bit of conventional wisdom here. The tank is mostly got storage available prior to a rain event, which adds to stormwater management. If you look at the first graph I showed you, the whole property is storing stormwater that's working with the rainwater tank. So it's the kitchen garden takes the rainwater overflows before it goes to the street. So it's actually producing more runoff volume changes. So the reliability of having, in my property in Newcastle, in having storage in the tank, storage available in the tank to stop stormwater runoff, or some of it, is more than 82%. So it's very reliable. Across the entire country, we've done research and taken measurements, and I'm showing some graphs here on this slide of, just suppose you have a rainwater storage between 1 and 10,000 litres, 1 and 10 kilolitres, and you use rainwater consistently for toilet and laundry uses as well as outdoor, you can actually count 50 to 70% of your tank volume as a contribution to what engineers called on-site detention. So it's saying that because the infrastructure is designed for probabilities, not for absolutes or averages. So is there going to be storage available in your rainwater tank if you use it for indoor uses prior to the event that the engineers used to design the stormwater pipes in your street, for example, or the detention basin at the bottom of your suburb? And that's how it's done. So the two graphs I'm showing here, the lower one is recurrence interval, which is ARI in years, 1 in so many year events, versus peak discharge, which is a metric engineers use to design pipes, for example, and pumps. And we can see here that the red line in that lower graph is what would happen in the property if there was no rainwater tank. The blue dotted line is the council standard, what they'd like to manage the runoff back to, which is what they perceive nature would have delivered in these types of events. The green line is if there was a 3 kilolitre rainwater tanks. And then there's the purple line, which is even lower, better performance, is 5 kilolitre rainwater tanks. And the next line down, it's the best performance, is 2 3 kilolitre rainwater tanks used at that property. As you can see, based on the way engineers design infrastructure, the rainwater harvesting system has produced the benefits when it's needed for the right design criteria, and it's better than not having them by a long way. The top graph on that slide, so the first graph was from Melbourne, the top graph on that slide is the available storage in your rainwater tank used for indoor and outdoor uses This was for a 3,000 litre tank prior to storm events used to design infrastructure again. So in that local government area, which was Geelong, they designed their stormwater infrastructure in the street for 10-year recurrence interval events. We now call it AEP. If you're an engineer, it used to be called ARI. As you can see, if you look at that graph and you go up to the blue line, you can see that for that particular type of event that the stormwater drainage system is designed for, that tank's going to have 2.1 cubic metres of storage available in it prior to rain events. So it'll create for each house that benefit. For a 100-year event, which is what the road surfaces are designed for to convey, not the pipes, which is the big event, big flood event people are really worried about, it's going to have about 2.7 cubic metres available, even though the tank is only 3,000 litres in this graph. And that's because that large event is a large summer thunderstorm that comes along when the tank is almost empty because it's dry. And this is my last slide, so I'm going to be quiet soon. It's the benefits of stormwater harvesting are quite significant. So this is some work we did for the Australian capital cities of the rainwater harvesting systems that are already in place. It was done in 2015. We have new work we're about to publish on this. So if you look across the capital cities, there's a fairly large reduction in megalitres, so million litres per year in stormwater runoff for the existing systems. It's far greater now. And across those capital cities, in the graph we can see 65,000 gigalitres, or 65 gigalitres or 65,200 megalitres of stormwater runoff for a year is not running off in an urban area or not causing flood and environmental damage as a consequence. And that's there hidden in plain sight. That's a benefit we're getting from people who have already done this. But if you look at the next columns on this graph, TSS is total suspended solids, TP is total phosphorus, and TN is total nitrogen. These contaminants are quite natural in our environment. Please be aware of that. But in excess loads, they're quite damaging to the environment. And as you can see, 13,000 tonnes of suspended solids per annum in 2015 were not discharged because of rainwater harvesting systems to waterways, 25 tonnes of phosphorus, and 172 tonnes of nitrogen was not discharged to waterways. They are very big numbers. For example, it costs something like $6,500 per kilogram to remove nitrogen via engineering methods from stormwater before it goes into waterways. So this is 172 tonnes, so I'll leave you to work that out, but it's a number like $50 million benefit just in nitrogen reduction per year. So it's a beneficial exercise. So thank you for listening. The key message here is rainwater tanks work on your properties with everything else to produce benefits to whole of society and to rural areas connected to your urban area, and to protect your waterways and your livability, provided you use the water. And if you're using rainwater for a regular indoor use, you're guaranteeing a stormwater benefit to your city.